Hi gentlemen, these will be your notes from Unit 0, Day 3. So a reminder, if you want to see the finished warm-up or review question or homework questions what we went over from class, just look at the finished notes. So today we're going to talk about the different types of functions, function notation. We'll talk about transformations on functions, and we'll talk about polynomial functions and their characteristics. So function notation, that's when you have the f of x and you have some sort of function. So like x squared minus 3, you could have g of x, which could be x plus 2 over x minus 1. So you have a quadratic function and a rational function. You could have h of x, which is a square root function, 2x, the square root of 2x minus 3. That is function notation. So we read this as f of x. It's more precise than just using y. So f of x, yes, you can just think of it as y, but it's more precise. It's telling you, especially if you think about it in terms of like physics, if you had v of t, it's telling you that velocity depends on time. So it's telling you who's the independent and dependent variable. So velocity, since it depends on time, it would be your dependent variable, and time would be your independent variable. So function notation is more specific than just using y equals. It's telling you who's the independent and dependent variable. So if you want to evaluate functions that are in function notation, so f of -3, this is just telling you that the x value is -3, so you're just going to substitute in -3. So this would be 3 minus -3 squared, which would be 3 minus -3 times -3 is 9, and 3 minus 9 is -6. C would be what we would call a composition of functions. So you're going to start with the inside and then work your way out. So you can try G and check it against the finished notes. So f of g of x, well, we're going to take g of x and substitute it in for the x in f of x. So this would be 3 minus 2x minus 1 squared. And then, yes, we do have to simplify this. When you're squaring a binomial, that means that you are writing it twice and then multiplying it out. So this would be 3 minus 4x squared minus 4x plus 1. And then we would distribute that negative. So 3 minus 4x squared plus 4x minus 1. Combine like terms, and we would get negative 4x squared plus 4x plus 2. If we're going to do a composition of functions with 0, first we're going to take 0 and plug it into f. So this would be g at 3 minus 0 squared. So I'm just taking 0 and plugging it into the f of x function. So this would be g at 3. Then take 3 and plug it into the g of x function. So this would be 2 times 3 minus 1, which would be 5. We talked about domain and range of functions previously, so you guys can go ahead and see if you guys can do the domain and range for these two functions. We'll go over that first one together. It looks to be a square root function. The domain, the x values look to start at 3 and then continue on if there was an arrow. So we're going to start at 3 and then continue on to infinity, or you could say x is greater than or equal to 3. The range, again, are the y values. So my y values look to start at 0 and then they look to climb. So my range is going to go from 0 to infinity, or y is greater than or equal to 0. So you could use interval notation with the parentheses or inequality notation with the less than and greater than signs. So you guys can go ahead and try the domain and range on the next two, and you can check your answers against the finished notes. If we are going to find the domain and range algebraically, that's kind of harder to do. What I really recommend doing is graphing. So you guys can either graph these by hand if you know what they're going to look like, or you can use Desmos. So if the first one I know that is going to be a sad parabola that moved 1 up. So we've got 1 up, and then we just have our sad parabola. So I know what that one looks like relatively quickly without having to use Desmos. So I'm going to graph that. And then his domain, since it is a quadratic function, the domain is all real numbers, or you can go from negative infinity to positive infinity. And then the range, the y values start at 1 and then go down to negative infinity. So negative infinity to 1. When you're doing interval notation, it's the smallest to the biggest. So the smallest number will go on the left, the biggest number will go on the right. Or y is less than or equal to 1. For B, go ahead and graph this on Desmos, and then see if you guys can come up with the domain and range of B, and then you guys can check it against the finished notes. Parent functions, we went through that worksheet in the Unit 0 Day 1 notes, so you guys can go ahead and go back and look through those. I may have deleted it. I did delete it. So you guys can go back and look at those parent functions that we went through on that sheet. But let's talk about a different type of function, a polynomial function. So a polynomial function, a quadratic function is polynomial, but typically when we think about polynomial functions, we think about any type of function that has exponents that aren't negatives, that are just whole number exponents and that aren't fractions. So 2x to the fourth minus 3x squared plus 1 would be a polynomial function. So let's go ahead and see what this guy's graph would look like on Desmos. So 2x to the fourth minus 3x squared plus 1. So 2x to the fourth minus 3x squared plus 1. And so he kind of looks like a W. So I'm going to take that graph and I'm just going to sketch him into here. So he looks like this, kind of, maybe. And that would be our polynomial function. So on the next couple slides, we're going to talk about some specific things about polynomial function. So you guys probably remember these points right here. We call those the x-intercepts. We can also call them the roots or the zeros of the polynomial. So wherever the graph crosses the x-axis, those are the x-intercepts. But we can also call them the roots or the zeros of the function. Where it crosses the y-axis would be the y-intercept. We also have these points, this point, and this point. Those are called maximums and minimums. We can also call them local maximums or local minimums if they're not the overall lowest or overall highest points on the graph. We also have something called end behavior. End behavior tells you which direction the tails are pointed in. So notice both of my tails of my graph are going up and up. So the end behavior is up, up. You can say it like that, or increasing, increasing. We can also talk about whether a graph is increasing or decreasing. And when we're talking about increasing or decreasing, reread it like a story from left to right. So if I start on this graph, my graph is falling until I get to that local minimum right there. So this would be decreasing. So my graph is decreasing that whole time. Once I get to that local minimum, the graph changes and it starts to rise. So from that local minimum to the local maximum, the graph is increasing on those values. And then after that, notice it starts to fall again. So the graph is decreasing between that maximum and that minimum. And then to end, the graph is increasing for the rest of its history. So those are some key components of polynomial functions. We're going to talk about its zeros or x-intercepts. We'll talk about its y-intercepts. We'll talk about the mins and maxes. We'll talk about its end behavior and its intervals of increasing and decreasing. So zeros and end behavior. So let's go ahead and look at a different function. So let's say we have y equals negative 2x to the fifth minus 3x to the fourth plus 2x minus 3. And we want to talk about the zeros and end behavior of this graph. So let's go ahead and go into Desmos and graph this. So negative 2x to the fifth minus 3x to the fourth plus 2x minus 3. So negative 2x to the fifth plus 3x to the fourth minus 2x plus 3. I think that's what I had. Minus 3x to the fourth plus 2x minus 3. So that's a minus. And then plus 2x and minus 3. All right. So here is that graph. So it looks to fall and then kind of do a weird rise below the x-axis and then fall again. So let's sketch that really quick. So it kind of looks like that. So this would be my 0 or my x-intercept. So the easiest way to find these are obviously on Desmos. So if I go to Desmos and I just click on that dot, that would be my 0. So the 0 on this graph is negative 1.809. So this is the point, negative 1.8090. So that would be my 0 or my x-intercept. The end behavior of this graph, notice this tail is going up and this tail is going down. So the end behavior, we could say up, down. there's an easy way to talk about end behavior. So as long as you remember even and odd functions like x squared, so that's an even exponent, you guys all know what x squared looks like. It looks like a happy parabola, right? And notice both of his tails are up and up. So if it's a positive x squared, the end behavior is going to be up, up. If it's negative x squared, you guys probably remember that, that would be a sad parabola. And if you look at his tails are down, down. So his end behavior would be down, down. It's the odd functions which have different end behavior. So if I look at x cubed, you guys remember from your parent function worksheet, it looked like a snake. And so if it's positive x cubed, his end behavior is down, up. On the left-hand side, the tail is down. On the right-hand side, the tail is up. If it's negative x cubed, it's a snake going in the other direction. So it would be a snake whose first tail is up and second tail is down. So his end behavior would be up, down. So you could graph on Desmos, or you could just remember how to do it based on whether the exponent, the degree of the polynomial or the highest exponent is even or odd, and then if the leading coefficient is positive or negative. All right, intervals of increase and decrease. Increase is where the graph is climbing. Decrease is where the graph is falling. And remember, you have to do it from left to right. So you're reading it like a story. So if I go back and let's just do this function, but let's change that one thing. So negative 2x to the 5th, negative 3x to the 4th, and then let's change this to plus 2x plus 3. So I'm going to go back to Desmos and change this to, oh, let's change that to a minus 3x. That's what I want to do. And then a plus 3. No, that's not what I want to do. Maybe plus 3x to the 4th, plus 2x, minus 3. There we go. So we're going to do negative, positive, positive, negative. So we're going to change this to negative, positive, positive, negative. All right, so if we're going to talk about increasing and decreasing, notice that if I'm starting on the left-hand side of the graph, it is decreasing until that point right there. That point is going to be called the local minimum because it's a low point on the graph in that little region. So my graph is decreasing, and we talk about increasing and decreasing as it's going towards along the x-axis. So it looks like this, kind of. And so my graph is decreasing all the way to this point. So this would be decreasing. And we name it on the x-axis. So it's decreasing from negative infinity on the x-axis all the way to that value, which was negative 0.409, I believe. So my graph was decreasing on the x-axis, so those are x values, from negative infinity to negative 4.09. 4.91. I got to change that. And then after that, it's increasing between negative 0.491 to 1.293. And again, so the graph is climbing there. So from here to here, and this is 2.931, I believe, and then this was negative 4.91. So then my graph is increasing right here, because the graph is climbing. So it's increasing from negative 4.91 on the x-axis to 2.93 on the x-axis. And then if you notice after that, my graph falls for the rest of the time. So that is decreasing. So it's decreasing from 2.931 on the x-axis all the way to infinity on the x-axis. Again, the intervals are named with x values, not y values. So if I go back, let's just make sure I had that. 1.293. So we got to change those. 1.293. And that's 1.293. And that is 1.293. And that's how we talk about intervals of increase and decrease, where the graph is rising and where it's falling. Absolute, global, local, and relative extrema. So absolute or global extrema are the max and min on the graph. So if I had a graph that looks like this, the highest value that this graph is going to go for the y value would be infinity. So his max value, his absolute max value, he doesn't have one because it's infinity, and infinity is not a real number. The lowest value that this graph would take on, and again, his tail goes all the way down, so his lowest value would be negative infinity. So he doesn't have an absolute minimum because negative infinity is not a real number. But the other 2 points, so the little hills and valleys, we call those local or relative extrema. So those are like the hills and valleys. So let's just say that this is the point -3, -4. So this would be a local minimum, or you could call it a relative minimum. And then let's just call this the point 3,2. That would be a local maximum because it is a peak in the graph, or you can call it a relative maximum. So if we go back to our Desmos graphs, those points right there that are on there, -0.491, -3.751, that would be a local minimum. And then the point next to it, 1.293, 0.743 would be a local maximum. So using your calculator to find extrema, we just did that on Desmos. So I'm letting you guys use Desmos this year. So you could just use Desmos to find local extrema. So let's say we had y equals 5x to the fourth minus 2x to the third plus 2x minus 1. Why don't you guys try and graph that on Desmos and tell me about the extrema of the graph? The absolute maximum, absolute minimum, local minimums, local maximums. All right, so graphing functions, the trig functions, they're basic ones. You go ahead and see the parent function worksheet. We did those in our last class. We did sine, cosine, and tangent. And then the reciprocal functions, secant, cosecant, and cotangent, you guys can see what their graphs look like on Desmos. Piecewise functions. So for some reason, these are everybody's least favorite. So if I had f of x equals, and now the graph is going to come in pieces. Let's say it's 3x minus 2 if x is less than or equal to -1. Let's say it's x squared if x is between -1 and 2. And let's say it is -x plus 4 if x is greater than or equal to 2. And we want to graph this piecewise function. You're just going to graph it in pieces. So I always just make a table of values for each piece. So let's start with 3x minus 2. So if I have y equals 3x minus 2, and then I'm going to make a table of values. The biggest value x can take on is -1, and then it can take on values smaller than that. Since I know that 3x minus 2 is a line, I just need 2 points to make that line. So let's plug in -1. So this would be 3 times -1 minus 2. So this would be -5. So I know I have the point -1, -5. 1, 2, 3, 4, 5. Notice that its x is less than or equal to -1. So this is going to be a closed circle, just like I would on a number line. If I plug in -2, that's 3 times -2 minus 1, which would be -7. So I have the point -2, -7. And so that first part of the graph is just going to be that little line or ray right there. And now I'm going to do the same thing for the next 2 pieces of the graph. So if I have x squared, again, I can just make a table of values. And notice this time, I know that it's going to be a parabola, and my values are between -1 and 2. So I'm just going to do -1, 0, 1, and 2. So I get a good grasp of what the parabola would look like there. So if I plug in -1, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So I have -1, 1. Now notice both of these are just less than or greater than signs, so they're both going to be open circles. So that's -1, 1, 0, 0, 1, 1, and then 2, 4. Again, 2 is a boundary point, and since it's just x is less than 2, it's also going to be an open circle. So that would be the middle part of my piecewise function, would be that blue piece. And now my last piece is another line. I have -x plus 4 as long as x is greater than or equal to 2. So again, I can make a table of values, and the smallest value x can take on is 2, and then it can take on values of x that are bigger than that. So I'm going to use 2 and 3. So if I plug in 2, it would be -2 plus 4, which would be 2. If I plug in 3, it would be -3 plus 4 would be 1. So I have the point 2, 2. And again, it's greater than or equal to, so this is going to be a closed circle. And then 3, 1. And so That would be what my piecewise function looks like. Transformations. So knowing your parent functions and what they look like, graphing using transformations will be a lot easier if you know what your parent functions look like. So we can have vertical transformations or vertical shifts, and that's when you add or subtract from a function. So if our parent function is the square root of x, if I add 1, that would shift my function 1 up. If I subtracted 1, that would shift my function down 1. So those are vertical shifts. We could also do horizontal shifts. Whenever you want to move the graph horizontally, the transformations are going to be inside with the x. So they'll be inside parentheses or within the operation symbol, like the square root symbol. So if I had my square root function and I did x plus 1, it's actually going to move it 1 to the left, because if you wanted to solve, if you guys remember like conic sections and finding centers of things, it's always the opposite. And so this is actually going to shift my function 1 left. If I did f of x is the square root of x minus 1, this is actually going to shift my function right 1. So if I go back to Desmos, I can prove that to you. So if I wanted to graph the square root of x plus 1, notice it actually shifted that graph 1 to the left, not 1 to the right. So x plus 1, the square root of x plus 1, shifts the square root graph 1 to the left. So those are vertical and horizontal shifts. We can also have stretches and compressions. So if you think about these on parabolas, they either make the parabolas wider or narrower. So if I had y equals x squared as my parent function and I did 3x squared, that's going to be a vertical stretch by a factor of 3, which means you're going to stretch it up and down, which makes it skinnier. So that's going to make my parabola skinnier or narrower. If I had y equals 1/2 x squared, that's going to make the parabola grow slower. So we call this a vertical compression, and it's going to make your parabola wider. If we're going to do horizontal stretches and compressions, the easiest way to think about these are with the trig functions. So if I had y equals sine x and I wanted to do a horizontal stretch or compression, it's changing the period. So the way that you can see horizontal stretches and compressions the best are with the trig function. So remember, your normal period is 2 pi, and then you take 2 pi divided by whatever the b is. So this would be 2 pi over b. So the new period would be b. So that is going to be like if you took a slinky, that would be taking the slinky and compressing it so that the graph would go faster. Or if we had y equals sine of x over 3, notice it's inside with the x, so it's going to change it horizontally. And so it would be 2 pi over a third. So the new period would be 6 pi. That's going to be a horizontal stretch. You're stretching the slinky out. So stretches and compressions horizontally, the easiest way to see those are with the trig functions. You can also have reflections. So reflections reflect the entire graph over the x-axis or the y-axis. So if we're going to reflect over the x-axis, we could do y equals negative x squared, so it would be out in front. And so remember, that just takes your happy parabola and makes it sad. If you want to reflect over the y-axis, then it's going to be inside with the x. And again, the easiest way to see these, well, you could have something like y equals the sine of negative x. And what that's going to do is it's going to reflect the sine graph over the y-axis. And so it would look like this. So you're reflecting the sine graph over the y-axis. So you have vertical reflections, which would go up and down, or horizontal reflections that go left and right. Remember, left and right are always inside. Up and down would be on the outside. So we have vertical shifts, horizontal shifts, we have stretches and compressions, and we have reflections. So let's go ahead and look at some of these. So if we wanted to sketch a graph of these, so we have a square root function and it's -2 on the inside. So it would take the square root function. So you just take your parent function, which you should remember from our parent function worksheet, and it's just going to move it 2 to the right. So that's what this g of x equals the square root of x minus 2. It's just going to take the square root function and move it to the right. This one is going to take the cosine function. It's going to move it down 4. And then the number in front normally is a stretch, but for trig functions, that changes the amplitude. So my amplitude is going to change by 3. So if I were going to do this guy, I would take my entire cosine function, move it down 4. So that would be the new middle of my graph. And then the amplitude is 3, so it's going to go up 3 and down 3. So that would be the highest and lowest points that my cosine graph would go. And then if you remember from class, cosine starts up top. So I would start up top, and then cosine goes down, down, back up, and all the way up. So that would be one period of that cosine graph. Functions even and odd. How I remember these is an even function would be like x squared. So even functions are symmetric over the y-axis. So visually, that's how you can tell if a function is even. It's symmetric over the y-axis. So you can fold it in half perfectly over the y-axis. Or if you plug in an x value, so if you plug in like 2 and -2, you get the exact same y value. So if I have f of x equals x squared, and I plug in 2, f at 2 equals 4, f at -2 equals 4. Since they're the same, that function would be even. If we're talking about odd functions, the easiest odd function that I remember is the cubic function. So that's x cubed. The way that you can think about odd functions, if you take an odd function and you rotate it 180 degrees, it looks the exact same. So notice if I took the cubic function and turned it on its head, it still looks the exact same as the original function. So 180 degree rotation over the origin, and it looks the exact same. So that's like 180 degree rotation symmetry, or it's symmetric over the origin. To tell if a function's odd, again, you can plug in 2 and -2 and watch what's happened. So if I have f of x equals x cubed, if I plug in 2, I get 8. If I plug in -2, I get -8. So they're opposites. And that's how you can tell if a function is even or odd. So go ahead on these two, figure out if the functions are even, odd, or neither. You can either graph them or use the idea that we plug in 2 and -2 and see what happens. You can check those against your finished notes. Composition of functions we talked about briefly at the start of class. This would be like f of x equals x squared and g of x equals x plus 2 over x minus 3. So if I wanted to find f of g of x, we would take g and plug it into x. So I would take this and plug it in right there, and I would have x plus 2 over x minus 3 squared. And that would be f of g of x. We could also have g of f of x. So that would take f and plug it into the x values in g. So I would have x squared plus 2 over x squared minus 3, and that would be g of f of x. You can also do a composition of itself. So f of x. You would take x squared and plug it into x squared. So you would have x squared squared, or x to the 4th. Domain of composition of functions. Again, you guys could graph these to figure out the domain. But the domain, let's say we have f of x equals the square root of x minus 3, and g of x equals x plus 4 over x minus 5. So again, you could take f of g of x. So you could take this and plug it in for here. And so you would have the square root of x plus 4 over x minus 5 minus 3. So the domain for g of x is x can't equal 5. So whatever that domain is, it also works with the composition. So for the composition of functions, we know x can't equal 5 because that would make the denominator 0. for the x plus 4 over x minus 5 part. We also know that in a square root function, what's underneath has to be greater than or equal to 0. So x plus 4 over x minus 5 minus 3 has to be greater than or equal to 0. So we are going to find a common denominator. So we're going to do x minus 5, and I would have x plus 4 minus 3x plus 15 over x minus 5 has to be greater than or equal to 0. So combine like terms, and I have negative 2x plus 19 over x minus 5 has to be greater than or equal to 0. I can multiply both sides by x minus 5. I already know that x can't equal 5. So if I do that, 0 times anything is 0, so 2x plus 19 is greater than or equal to 0. Subtract the 19 over and divide by negative 2. Remember, when you divide an inequality by a negative, you flip the sign. So x has to be less than or equal to 19 over 2, and x can't be 5. So that would be the domain of that composition of functions. So just make sure that you test whatever you're plugging in. You need to find the domain of that, because that domain sticks for the composition of functions.